All right, so our second example is going to be page 706, number 26. Some crazy person wrote this series, sum n equals 1 to infinity of cosine of n pi over 3 over n factorial. So this is just the kind of thing that none of our other tests will work on, so we like to use the ratio test because it tends to work on a lot of things. So first I need to consider a sub n plus 1 over a sub n, and I'm just going to consider that separately again and add in the limit and the absolute value later. So what that is, well, first we're going to put in n plus 1, top and bottom. So we're just going to first put our a sub n plus 1 by going cosine of n plus 1 pi over 3. And then my denominator, I'm going to have n plus 1 factorial. So that is our a sub n plus 1 right there. And then we're going to go times 1 over a sub n. So that means we're just going to take this term and flip it over. So we're going to go times n factorial over cosine of n pi over 3. All right, so that's pretty weird looking, but at least we have some cancellation. Like you can think n factorial means, for example, 4 times 3 times 2 times 1, and then n plus 1 factorial is going to be 5 times 4 times 3 times 2 times 1. So everything's going to cancel out except the 5, the n plus 1. So what this ends up equaling is 1 over n plus 1 times cosine of n plus 1 pi over 3 over cosine of n pi over 3. So that's just canceling the n factorial with the n plus 1 factorial. So now, all right, so what are you going to do with that thing? So one thing we can do is start looking at the absolute value of a sub n plus 1 over a sub n. And so since I know that the 1 over n plus 1 part is positive, so I'll leave that out of the absolute value, and then I'll just look at the absolute value of the cosine of n plus 1 pi over 3 over cosine of n pi over 3. Now there's no way I can simplify this, that's the part that's an absolute value. There's no way I can simplify this wacky thing using analytic means. But if I just think about the unit circle, right? So I'm going to think about the unit circle. Let's put the little unit circle-y thing down here. All right, now we're going to think about what this means that I'm looking at n pi over 3. So let's look at the bottom term first, and then the top term is going to come out. So if I look at cosine of n pi over 3, first I'm going to be looking at 1 pi over 3, and then I'm going to be looking at 2 pi over 3, and then we're looking with 3 pi over 3, and then 4 pi over 3, and then 5 pi over 3, and 6 pi over 3, and it's going to keep going around. So that's what cosine of n pi over 3 is going to be. Now cosine is the x-coordinate of these points, so this denominator can only be 1 or 1/2 or negative 1/2 or negative 1 or 1/2, negative 1/2 again or 1/2 again. So that's what the denominator can be. Now the numerator is just n plus 1 pi over 3, so wherever the denominator is, the numerator is like one step ahead of it. So as the n increases, we have, this is the denominator numerator, then denominator numerator, then denominator numerator. We just keep going around the circle. All right, so it doesn't take too much analysis, though, to figure out that the largest the top could be is 1, and the smallest the bottom could be is 1/2, and we're going to forget about the positive and negative because it's absolute value. So I'm always going to be either looking at 1/2 over 1 or 1 over 1/2. The largest of those things is 1 over 1/2, which is 2. So this whole thing then is less than or equal to 2 over n plus 1, because this whole expression is less than or equal to 2. And that's the sort of key to this whole thing. So then you can add into this, sort of observe that my absolute value is always going to be positive. And then you can say, what about the limit as n approaches infinity of this stuff? Well, the limit as n approaches infinity of, if I just look at this end of my inequality, I have 0. And if I just look at the other end the inequality, I have limit as n approaches infinity of 2 over n plus 1. And the limit of 2 over n plus 1 is equal to 0 because denominator increases without bound. Limit as n approaches infinity of 0, that's the limit of a constant sequence, so it's just the constant. So it's also equal to 0. These two are equal to 0. So then it follows that the limit as n approaches infinity of 1 over n plus 1, absolute value of cosine of n plus 1, sorry to get all these parentheses in here, pi over 3 over cosine of n pi over 3, that whole limit is also 0 because that limit is trapped in between these two endpoints, which are both going to 0. So that's our famous sandwich theorem. That is the sandwich theorem. Sandwich theorem. All right, so now I know that this limit is 0, but that limit was the limit of absolute value of a sub n plus 1 over a sub n. So now we have limit as n approaches infinity of absolute value of a sub n plus 1 over a sub n, which is this, equals 0. And what we like about the number 0 is that it is less than 1. So for the ratio test, all you need the limit to come out to be is less than 1. And in fact, it is less than 1. So I get to conclude that not only does the sum from n equals 1 to infinity of cosine of n pi over 3 over n factorial converge, it also converges absolutely. Converges absolutely by the ratio test. So not only do I know that this series, which has some positive and some negative terms, because cosine keeps going positive and negative, not only does that series converge, but also if I took the absolute value, it would still converge. Converges absolutely, the ratio test always gives me that, converges absolutely. And in fact, any series that converges absolutely also converges, so it also converges. But it's a stronger thing to say it converges absolutely. And by the way, I could have said that also back here on number 24. We said that one diverged, so we didn't have to say absolutely because it diverged. So our number 24 diverged by ratio test because the limit in question was greater than 1. Now I have a limit that's less than 1. So not only do I get to say that the series converges, but it converges absolutely. So that is how you use the ratio test. And here is your homework. It is Kokoska-Stewart, Stewart, section 9.6, page 706, number 11 to 31 odd. Follow these examples. Look for the solutions to be posted. This is going to be due next Friday, March 27th.